drawn the diagram for diffraction? Yes. So, if you see here, light from an infinite distance, it is reaching the convex lens. Okay, light from an infinite distance, maybe a point source. Okay, so when it reaches the convex lens, what will happen? If it reaches light from a point source, if it reaches the convex lens, what will happen? After reaching the convex lens, it will start to move parallel. Am I right? So that's the case happening here, where the rays are parallel. Okay, and here if you see, these parallel rays are coming from the source. That's enough if you draw. Okay, no need to draw this convex lens and the point source. Okay, so as rays are coming from the point source, small a is the width of the slit. Okay, small a is the distance between the two sources, and if you see here, from this source, what kind of wavelength will reach? Will come out from the source. These rays are parallel. Am I right? So from parallel rays, what kind of wavelength will you get? Okay, primary, secondary. Whether it may be a circular wavelength or a spherical wavelength or plane wavelength. Plane wavelength. Are you all sure? Yes, very good. So since the light rays are coming parallel from the source, you will be getting a plane wavelength. Am I right? So when the plane wavelength reaches this slit, if you see here, this is a cardboard and a single slit is made here. This is a cardboard and a single slit with larger distance is made here, and the plane wavefront, when it's reaching here, so what will happen? If the plane wavefront reaches here, yes, discussed, all the points that are present on the plane wavefront will act as, very good, will act as sources, will start to act as sources. Okay, get inside. So when the plane wavefront, when it reaches from the source, each and every point that lies on the plane wavefront will start to behave as sources. If you see, it will be like that. Can you remember this plane wavefront? How the day I have discussed in the primary wavefront, how a secondary wavefront is produced? Sabarish, listen here. Can you remember? From this primary wavefront, what kind of wavelets will be produced? Very good, secondary wavelets. From the secondary wavelets, if you draw a common tangent plane, what will you be getting? Secondary wavelength. Very good, you all remember this. Okay. So I am proceeding now. I am going to consider just 3 points from the plane wavelength. Okay, not all the points. I am just going to consider only 3 points from the plane wavelength. So that I will be naming as L, M and N. Okay, these points are named as L, M and N. Okay, here the screen is not like interference pattern, where the slit and the screen is separated by a distance capital D. Yesterday, can you remember the distance between the slit and the screen when we are discussing in case of interference is capital D. But here the screen is kept at a very large distance. Okay, so here the screen will be somewhat a larger distance and to C. I am naming that point as C. Okay, so if light rays can move here and there, am I right? Not only on the straight line, it can move on this side also. So when a number of rays are coming from the sources, am I right? So how a ray will be moving is, in this case from a plane wavefront, the rays will be emanating like this. Emanating means coming out. Okay, rays will be coming out like this and they will go and fall on the screen. Okay, so that only in case of diffraction, when they are falling on the screen, at the central part you will be getting a maximum, a fringe, central bright fringe of maximum width. Can you all see in the intensity pattern that's given in the diagram? You can notice a fringe fringe having maximum width, central bright fringe. Center you will be getting a bright fringe. While at the center there will be no phase difference between the waves. Since there is no phase difference, according to our constructive interference rule, you will be getting a bright fringe. Since there is no phase difference. So that only in case of diffraction you will be getting a central bright fringe, and continuously how you are getting fringes of decreasing. Which one is decreasing in this fringe? Can you say? Intensity is decreasing, am I right? This amplitude is decreasing here, am I right? Continuously it will be decreasing. Okay, you see this is your amplitude, am I right, Srinivas? So in the consequent fringes, your amplitude will be decreasing, and that too at the center you will be getting a bright fringe. Why? Because all the waves, when they are going and reaching the faraway screen, at the center you will be getting a bright fringe, and at this point this will be reduced in intensity. So that okay, comparing to here, you will be getting more intensity waves here. So here the intensity will be more for the fringes. Okay. So coming to this point, I am erasing all those things. I will be showing the animation also, how in diffraction waves are emanating outside from the source. So if you consider straight waves on a straight line, it will be 2c. Okay. If you consider to some other point P, an arbitrary point P. Yesterday we have considered for interference. Am I right? Like that, if you consider for P, can you all understand that this ray is making some angle theta with this ray? This original ray that is moving straight is making some angle theta that is moving towards P. Yes. So what can I say now? To find that, what is our main goal in diffraction and interference? Our main goal in diffraction and interference. Yesterday, after drawing the diagram, I wrote an equation. Yes? Yes, path difference. To find out the path difference. In both the cases, in interference and diffraction, I have to find the path difference. Okay? So, here also, can you see, there is some path difference between these two lines. I am drawing here in a simple manner that the rays towards C is looking like this and towards P is looking like this. Can you see some path is differing in between this? Can you see? This path difference I have to find in this case. Okay.